Yo, this is the menace cat. Uh, so, why am I doing this? There's no strong reason for this stream. Um, I do have an optional final exam coming on Tuesday, and perhaps the reason why I'm doing this is to test my willpower to see if I can push myself to study when there are no clear incentives to study. So maybe that's the reason. I already cleared the exam. I already cleared the subject with like a B grade. I could study a bit harder and try to get an A grade maybe. Not that I need to. It's just optional. But you know, it still would not sit right with me if I don't try. You know. So, anyways, it's a bit too late, I guess, to even try. So it's like I think 11. Let's see what the time is. Okay, I'm in Atlanta, so it's 11:15 right now. Okay, so I don't have a time limit in mind on how long I wanna stream. I'm just doing this to keep myself accountable and observe myself later on and see how I study. Anyways, 11:15. So let's start. A lot of this is not gonna be visible to you folks, but anyways, right? Um, let's see. Okay, let's go to paste bin. No, you know what? I hate that paste bin has such a painful UI. Like it's okay. The UI ain't bad. It's just the ads. They annoy me a lot. Of course, they gotta make money, but anyways. Uh, Notepad online. Very suspicious, but sure. Dude, this is actually so clean. Ah, fucking assholes. They had to put an ad in here, which is very annoying. Anyways, so let's just see. Is there no like full screen version? Oh, dude, this is what I needed. This is exactly what I needed. Okay. 6515. Cool. So this is going to be like a study plan. Let's do like a timestamp. This is how I usually conduct interviews, but timestamping is such a goated technique. Just gives you an idea of where you are losing time. Started making a study plan. Cool. So let's see. I'm just gonna go to the other browser. I'm gonna go to resources. I'm gonna open up a few PDFs, I guess. This is one. Fast Fourier search. Okay, so I have like 6 to go through. Polynomial multiplication is one. Fast Fourier transform is another one. Topological sort is another one. And search and distance algorithms are another one. Okay, cool. So I'm just gonna start opening each PDF here. These are like my class notes. It's okay to make them public because they are anyways public, accessible to all, so it's fine. So I just want to move it into like a single tab. How do I do that? Yeah, perfect. Okay. Notes, I guess. Divide and conquer. This is fine. cool. So getting the rest of my notes. I think this one's polynomial multiplication, fine. Closing these three. Then I believe there is fast Fourier transform. Let's put this in here. And then there is DFS and BFS, fine, I guess. BFS and DFS, and fine, that's good. And then there are search algorithms. So okay, cool. Oh my god, just make it better, please. Okay, awesome sauce. Cool. So let's see. I have my notes organized here. Dude, this is such a fucking annoying ad. Fuck you. But I get it. OnlineNotepad.org. You're still, you know what, dude? Sure, this is fine. What I could do is I could just simply make my own editor and host it online, not have any ads whatsoever, and just, let people use it. Sure, there are font families, which is pretty decent, I guess. Well, sizes. Actually, this is a pretty hard thing to implement, honestly. This is the type of shit that I think should be like forever free, Anyways, let's see. Okay, let me first quickly go through some of my flashcards. Y'all won't see it, but they're there. Merge sort. Okay, see, all merges in ith layer take this much time. Okay, so fill in the blank merge sort, like flashcard. Why am I doing flashcards in the middle? Because before the day ends, I at least go through like 20 flashcards or 10 flashcards. I'm just gonna go through 10 remaining flashcard quotas that I have to fill. Let's see, merge sort. Say all merges in ith layer take this much time. I think it's like a big O of, I believe it's like n by b to the power I times a to the power I. I know that n by b to the power I is the size of the input at the ith layer. A to the power I is like the vertices, like basically the number of splits in which your recursive function would be splitting into. So anyway, like if you imagine it as, if you imagine the recursion tree as some sort of graph, then the vertices, the ith layer is going to have a to the power I nodes, ith layer, and each node, like the total node work is going to be n by b to the power I. Why n by b to the power I? N is going to be the input at the top level, and b is like the size by which the input shrinks at every recursive call, and you keep doing that repeatedly. It's just going to keep recursively piling up, and then it's just going to keep dividing. It's going to keep shrinking the original input by a factor of b to the power I. So that's what I think it is. Oh shit, I forgot about the factor of c. I kind of had it somewhere in my mind, but okay, this is going to be a hard one, so I'm going to do it hard. So LP algebra for max LP. So what is the algebra form for max LP? It should be max of C transpose X such that A transpose X is less than equal to B and X is greater than equal to 0. Wait, is that what they want from LP form? Oh, okay, okay. Sure. Oh, okay. Sure, okay, got it. Sure, easy, I guess. Hard, actually. When A equals B to the power, this is about Master's theorem. If A equals B to the power C, then what is the runtime for Tn equals A times, okay, I get it. Well, this is classic Master's theorem. I forgot about it, but I had it on my cheat sheet somewhere. Let's see, there are a bunch of cases. I think it should be just. I don't know. I don't know. Okay, NC login. Hard. Hard. What does complementary slackness theorem say? The complementary slackness theorem says that yj times A transpose x minus b is going to be less than 0, or xj times C transpose, not C transpose, my bad, Y transpose A minus C is less than 0, right? Let's see. The official definition is, for each primal constraint AI x less than bi, the product yi, which is what I said, bi minus yi times the, in round brackets, bi minus ai transpose x equals 0, which is exactly what I said. And for each dual constraints, y transpose x greater than or equal to c transpose, the product xj times cj minus y transpose aj equals 0. Okay, perfect. I got it. If a primal constraint is not tight, the corresponding dual variable is 0. Okay. If the primal constraint is not tight, the corresponding dual variable is 0. Fair. If a dual constraint is not tight, the corresponding primal variable is 0. Okay. If primal constraint is not tight, what does that mean? What is a primal constraint? A primal constraint is if a primal constraint is not tight, then it means that when it says a primal constraint, it is referring to A transpose x less than or equal to b. That's basically the primal constraint. If it's not tight, it means it's not an exact equality. It's like an inequality. Then the corresponding dual variable is 0, right? A corresponding dual variable is yi. So that's what they're saying. If it's not tight, tightness just implies equality, right? Okay. So if a dual constraint is not tight, then the corresponding primal variable is 0. Okay, these conditions are necessary and sufficient for optimality. Interesting. Oh, of course, these conditions being necessary and sufficient for optimality kind of stem from the weak or strong duality theorem, I would say. Anyways, explain the capacity scaling algorithm for max flow. Oh, wow. Capacity scaling. I didn't even know this. I don't know this, honestly. Let's just read through it. Okay, you set your flow f equals 0 and some capacity, delta equals some capacity, where c is currently the max capacity. Okay. Your flows are going to be 0 first. Then there's going to be some delta, which is going to be set to some c. Okay. Well, delta is greater than 0. Well, delta is greater than 1. Okay, so hold on. What is f? F is your flow. Initially, it's 0. You use some capacity, delta. You use some delta and you set it to the max capacity in your graph. And while your delta is greater than 1, we build a residual graph and exclude any edge that is not at least delta. Okay, this part is straightforward. You try to find an augmenting path, and if we do find an augmenting path, we update f as f plus p times delta. Okay, and go to 2. Okay, makes sense. If no augmenting path, then update delta by 2. Okay, return f. The runtime for this is m plus n m log c. Okay, this is interesting. C is the max capacity. This is going to be hard. So anyways, if a is less than b to the power c, what does that mean? If a is less than b to the power c, then the runtime for Tn equals a times Tn by b plus bgo of n to the power c. Okay. Hold on. What this means is, suppose the number of, if in a recursive call, if the input is, if the input is not growing, is not being split faster Okay, if the input is not shrinking faster than the subcalls, right? So what does that mean? What this means is you are making more splits in your recursive call, but with every split, after every split, there is going to be some amount of input that is going to be overlapping between multiple splits on some ith level. And if you let this, okay, and if you try to find, if you unroll this equation and try to see where this goes to, then I would say that this would give you big O of n to the power c. That should be your time complexity, I guess. Perfect, perfect. That's the time complexity. Easy, I'll say. Okay, this merge sort question came again. Merge sort, say all merges in ith layer take this much time. Big O of, let's see, what was it? Okay, it should be a big O of, in parenthesis, n by b to the power I, the whole thing to the power c times a to the power I. So n by b to the power I is the input size at the ith layer. A to the power I are the number of vertices at ith layer. So I guess that should be it. And c is, of course, it's that depth. Perfect, perfect. Easy, I'll say. Okay, strong NP hard versus weak NP hard problems. Okay. So strong NP hard problems are problems that cannot be even verified in polynomial time, like 3 sat, for example. Weak NP hard problems are problems that can be verified for small input sizes. Like, oh, okay, hold on. I may be wrong here. I know that strong NP hard problems are problems that cannot be efficiently solved even for a small input size, right? That's the thing. Like, even if you do very small input size, you can't solve it efficiently. That's like 3 sort problem, for example, is one that I know of. And weak NP hard are those that can be solved in pseudo polynomial time, I think, for small input sizes. And I think that's just like knapsack maybe. Let's see what the answer is. Okay, the real answer is strong NP hard problems that do not have pseudo polynomial time algorithm for even small inputs. What I said, weak NP hard problems that do not have pseudo polynomial time algorithm for small inputs. Knapsack and suppress sum. Okay, perfect, dude. This is perfect. So I would say this is easy. Because I got it. So if a equals b to the power c, we already saw this master's theorem thing. It's like n to the power c log n. That's the upper bound. Okay, perfect, easy. What is the definition of small omega notation? So I know that, let's see, let's try to recall. I know that big O is upper bound, small o is strict upper bound. So small omega should be reverse. It should mean that f of n is strictly greater than g of n. If f of n is like small omega notation g of n, then it means that f of n is always greater than g of n. And I think it should also be that the limit of g of n by f of n should be like 0 if n tends to infinity. Hold on, does that make sense? Let me try to think. So I'm saying that f of n is always greater than g of n. And if n tends to infinity, then I am saying that my f of n grows much faster than g of n. So g of n by f of n, when n tends to infinity, should be 0. Yeah, I think that should be the case. Okay, perfect. This is perfect. I'll say easy. Okay, if a is greater than b to the power c, then what is the runtime for t? Okay, perfect. This is the third case for Master's theorem where a is greater than b to the power c. What this means is you're merging, you're splitting your function faster than you're splitting your function more than the amount of input that you're sending to the like recursive function call. Is that even like an eloquent way of saying it? Okay, let's see. What I'm saying is, if I have a function that recursively calls itself, and recursively it makes some a calls to itself, and for every call it shrinks its input by b, by a factor of b, and I'm saying that a is much greater than b to the power c, then how does it affect my time complexity? I know the answer to this is, I just know it. I cannot. Uh, I just know that it's just n to the power log of uh, something to the base b a, something of that sort. I don't exactly even remember the definition. Can I do it from first principles, I wonder? I don't know. I could. Okay, so it was n to the power log of a. That's what I had. Hard, I'll say Ford-Fulkerson algorithm. Okay, let's see Ford-Fulkerson algorithm. How does it work? You first take a graph, you set your float as 0. You take your graph, you create a residual graph first of all. How do you construct a residual graph? You create a residual graph by finding the min capacity. Like you find a capacity C in your graph and then update all your edges by, like, you find some ST path. Okay, you find some ST path. Okay, wait, hold on, is that how you do it? Not really, right? You first construct a residual. That's the primary thing, right? But doesn't residual, how do you get the capacity when you want to find a residual? I'm just doing a recap, so it's gonna be a bit slow. It's gonna be a bit foggy in my head. Okay, you have a flow vector. It's gonna be 0 right now. We've been given a graph, you know the weights of the graph. You need to construct a residual graph. For a residual graph, you need to have some capacity, right? Okay, so here's what I'm going to say. You find some ST path in the graph. Okay, from source to the sink. S is the source, T is the sink. Find some ST path. Along that ST path, find whatever is the min capacity maybe, and update the all the edges by that min capacity. Is it just along the ST path? I wonder. I think so. I could be wrong. It's all very foggy right now, but maybe. And once you do that, you create a back edge uh, for that path and make everything as minus of C. Not minus of C, just the direction of the edge is gonna be the reverse, but the capacity is still gonna be C. And then you keep doing that till you keep doing this until you find like more and more ST paths, and then eventually you'll arrive at a moment where there will be no more ST paths, and that's when you would have arrived, right? I think that's when you arrive. Cool. So when you find no more ST paths, that's when you have arrived at the max flow apparently. And so yeah, like you start with an empty flow, you find an ST path, you construct a residual graph, you keep finding ST paths on your graph as long as you can. Once you are no longer able to find more ST paths, that's when you are done with your Ford-Fulkerson algorithm. Now the sum of the flow that is going to the sink or going to the source, that is going to be your max flow. And that's the Ford-Fulkerson algorithm, and I think this takes, I think the finding of the ST path takes big O of some m plus n, and because because your max flow could be like some n or something, you could take like some n time. So it's just like, it's quadratic is what I know, but let's see. Okay, so the actual answer is you set FE to 0, so set flow to all. You create a residual graph, check for ST path in GFF. If no such path, then output F. Given P, let CP be the min capacity along the path in GF. Perfect. Augment F by CP units along path P, just along the path P. That's perfect. Repeat until no such ST path. Perfect. Good. I would say just good. Okay, fully polynomial time algorithm for a knapsack. Okay, that's an interesting one. So it's pretty straightforward. You assume some epsilon. That's the approximation that you want. You create a theta. You define a theta, which is given by epsilon times V max. V max is going to be the max value in your knapsack by n. N is going to be the total number of items in your knapsack. And then you do you create a V bar V bar is going to be a set of weights, which is going to be defined as V bar I is the ceiling of Vi by theta uh, times theta. Theta would be again outside. And once you have defined this bar, you apply your knapsack on this new V bar. And once you have applied knapsack on your V bar, you essentially get your solution to, like, you get like a approximate fully polynomial time solution. And if you were to analyze the time complexity, you would notice that this would be like a big O of some n squared times theta, I guess. Theta would be defined as not really. Hold on. I think it will be n squared by theta or something. I don't know. I need to figure out the time complexity part. Let's see. Okay, so I got the steps right. The time complexity, okay, the time complexity is n squared times V max, which is kind of not what I said, but fine. Because that's the time complexity of knapsack in general, okay. N squared times V max by theta, you just keep unrolling it, and you know V bar max is defined as n by epsilon, which is just n cubed by epsilon. Okay, perfect. This algorithm is polynomial in n and linear in 1 by epsilon. Okay, yeah, makes sense. Easy. This is actually hard, but whatever, right? Okay, if a greater than b, okay, so the time complex, again, just another flashcard. So it's gonna be big O of a to the power, n to the power log of a to the base c. It's gonna be a big O of n to the power log of a to the power base b. Okay, easy, that's easy. Let's see. What is the time complexity of fast Fourier transform? It's d log d, where d is like the degree of polynomial. Perfect. Easy. L can be negative value, false. In Lipschitz or in L Lipschitz or anything else, L cannot be a negative value. So L Lipschitz and L smooth, L cannot be a negative value. Easy. So I finished my flashcards. Let's see how many flashcards I finished today. I did 16 reviews right now. I can just create more as I go. But okay, anyway, so let's see. Let's see. Actually, you know what? A better way is this. Yeah, this is. Yeah. So 41 p.m. Got by pending flashcard reviews. Cool, so I'm done with my flashcards right now. Okay, cool. But anyway, just 11:42 p.m. Started planning again. Okay, let's create a plan in general. Study plan. So the flashcards that I did, they coincidentally were for Grad Algos because they were due, but in general, I do flashcards from like a variety of topics. This is just like one of them. Anyways, let's see. 11:43 p.m. maybe. What am I doing? I don't need this, right? Okay, so we could do sequential stuff. 1, 2, 3, 4, 5, 6. Okay, so finish going through PDFs 01 to 06, and I believe this is from divide and conk to source algos. Okay, cool. So we need to do these, but how? Okay, sure. If you do go through these, retention strategy, right? Uh, Come on, dog. So what is going to be my retention strategy? So fair, like I can go through these PDFs, but I know that I'm going to be able to uh, go through them pretty quickly because I've already seen them and the notes are not too big either. So my retention strategy, right? Like I could blog about them, right? Blog about them. Uh, that's like one because I'm anyways writing like a recap blog. I'm not gonna bullet this. Um, oh, add flashcards if I've missed them. Uh, Locate them on your uh, cheat sheet. Actually, uh, the best. Oh, the best retention strategy would be test yourself on these topics. So I could just test myself. Uh, Review exam 1 mistakes. Cool. So I'll also review my exam 1 mistakes while going through them. Actually, the exams for this are pretty easy. That's what I'll say. But anyways, let's see. I don't need this. I want like sample exams for this. Exam 1 solutions maybe. Yeah, I'm just gonna paste it here. So here is what I can aim to do today. I can try to finish Yep, okay. I can try to finish the first unit and I will see what to do next, right? So I'm gonna order the priority like this because I've always wanted to add this to my blog. Cool, so I'll just do these three things, I guess. Let's go. Let's go to okay. So 3 divide and conquer, and then search algorithm. It shouldn't be too long, I guess, but let's see. Let me just check if my stream is doing well. Okay, algorithms can be described at different levels. Okay, this is just like bullshit about not bullshit. This is amazing. These are amazing notes, but these are just like we don't need to get into this. This is just like very gentle intro. These are the definitions that we need to work on. Okay, count the number of elementary operations. Use the bigger notations, make counting easier, ignore constant factors. Okay, perfect. Okay, so here's what I will say. Um, do not, okay, redundant because I will add to blog. Pointless. No, actually, this is also redundant. Same issue, cheese okay, redundant because I will add to blog. Cool. Okay, cool. So let's see. Blog about them. We best test yourself on these topics. Add flashcards if I've missed them. Okay, fine. Let's go back. Count the number of elementary operations. Fine. So I'm just gonna get my cheat sheet next to me because my cheat sheet contains some really good resources on how to you know Sorry, my cheat sheet in general has like some really good resources on how to organize my content and so on. Perfect. Perfect. My first cheat sheet is actually very small, so there shouldn't be much to put on the cheat sheet, right? Let's see. What are the first set of things that I need to put on? The first set of things that I need to put on my cheat sheet are the notations. Hold on, you know what? I'm wondering, I am wondering if I can use my iPad in some way to write this big ass cheat sheet and then upload that beautiful PDF or as an image or something on my uh, yeah big upload that PDF or something note somewhere on my. Oh wow, I didn't know you could do that. What the Sigma? Hold on, what happens if I can control my iPad with my mouse, it seems. I can control my notes with this. Okay, I can say new. I can go here, for example. Now the question is, can I drag this? Interesting. I can't drag this anywhere, right? Very interesting. Hold on. Uh, let me just Google this, I guess. Okay, hold on. Mac OS use iPad uh, as I know I'm already using it as a second screen, right? I don't need that. I'm just saying you use iPad to write and cast on. Okay, Mac OS use Apple Pencil and iPad to write. That's something I'm looking for. Okay. Okay, I need a way. Yeah, I need continuity markup basically, right? Okay. Oh, okay. There's apparently some continuity markup thing that can be done. Hold on, let's see. I'm gonna open something up. Downloads, maybe. Yeah, maybe just problem set, random problem set I can do. Edit, I guess. How do I edit this? Wait, how do I edit this? View. Um, show markup toolbar. Yep. Now they say that okay. Mac OS use iPad as stylus. Okay, there's something called as AstroPad. Let's see. Oh, again sidetracked. Just gotta note this down. Where am I losing time? I would wonder then. Figuring out ways to use iPad as a stylus. Cool. Okay, let's see. Come on, dog. Conti. Okay. Oh, hold on. Shut the fuck up, bro. AstroPad. I'm sure someone had come up with this. Okay, this is pretty good, honestly. Let's see what Astropad does. Okay, you can mirror your desktop display here. Okay. Okay, there's Astropad. What else is there? Continuity sketch. Let's see. Oh, come on, dude. Continuity sketch doesn't work. Sidecar. No. Okay, there's something called dual display, which is pretty cool. I'm gonna try to do a display because it looks pretty easy. Let's see if this works. Good. Otherwise, screw it. We'll just, use some old-fashioned ways, I guess. Allow, I guess. Get started. Continue. Continue. Okay, sure. Continue. Oh, come on, dog. Don't make me. Yeah, just let me sign in with Google. Come on, dude. Why can't you pick up my local Google instances? Shut up. I'm not doing that. Screw you, do it. You're decent, but you're promising. But anyway, screw this. Screw this. Okay. Hold on. I have another idea, I guess. Okay. Yeah. Let's see what is my OneNote account looking like right now. Student. Let's see. I had my OneNote account. Shut the fuck up, dude. What the fuck is this bullshit, bro? I have no idea what this bullshit is. I would never have written these things here. Why is it opening my Georgia Tech shit, bro? I don't want to use my Georgia Tech stuff here. Hold on. Home, Grad goes back, Shiv B. No, I don't want to use this, to be honest. I could do it here, I guess. Let's see, how do I add another account, right? Okay. Okay, my bad. Give me a second, bro. Oh, come on, dude. Should work now. Annoying. I don't know if it'll be real time, but let's see. No other people use it, so why? That's fine. Okay. Okay, that's fine. Okay, let's see. Deleting this section permanently, delete this section, delete this section, sure, delete this section permanently. Okay, let's create maybe a new notebook. No, I don't need this shit. No, come on, dog. Yeah. Screw this. I'm gonna create a new notebook. What is going on in my other thing? Okay, anyways. Let's see. Okay. Do I see this here though? No, hold on. Okay, I found a notebook. Now I'm gonna see if this works. This method that I'm about to try out, if this works, then great. No, dude, I don't want this shit. Hold on. Okay, I guess if I reload this, it should be fine here. Can I not have real-time editing? I'll just have to reload this, I guess. No, it didn't reflect here. Okay. So this method is not gonna work in general. This doesn't seem like a very useful way to do studies, but fine. Whatever, right? Home, I'll just go to home. I don't wanna go to these, honestly. Just gonna close this shit because it's just useless. Anyways, putting this aside, now what I'm gonna do is closing this shit. Okay, fine. So here is the deal. I tried going through things. I tried finding like an efficient way of doing things, but it did not work out as I expected it to work out. So I'm fine now. Okay. Okay, my bad, bro. My bad, bro. I should not have seen that. Okay, cool. So 12:03. It's 12:03. 12:03 a.m. Did not find an easy way to sort this. Okay, to use iPad as a stylus. So continuing with the usual flow. Cool. Awesome. Uh, we'll focus on blogging for retention. Anyways, so we spent like 10 minutes in this window just to figure out what you're doing with iPad or with our stylus. So we need to eliminate this window basically. Okay, like we need to eliminate this. This is bad. Like this window we need to minimize. Okay, cool. So let's just go through this. I have recognized already that the only important thing for the first PDF. So I see that there are these lemmas which just define the big O's, small O's, big omega, small omegas. Everything else in here is just a uh, it's like an example run. For example, it's like an example run of merge sort. For example, why am I saying example again? I need to be better at my buffer dialogue. I can't be like buffering and randomly saying bullshit. Anyway, so the only notable thing for first PDF is these runtime complexities. Maybe we can go through. Let's do that first, okay? So I know that, okay, what is big O of n? Big O of n is like upper bound. So I'm not gonna look at it. I'm just gonna try to recall it myself. Although I glanced through it, but fine. Big O of n is like an upper bound, which says that f of n, like some function with input n, uh, is equal to big O of g of n if f of n is less than or equal to some c times g of n, where c is some constant greater than 0 for some n, for all n greater than some base n, right? It essentially means that my g of n function grows much faster than my f of n, and g of n is going to be always the upper bound of f of n. And the way we essentially describe this is like if I were to take the ratio of f of n and g of n, like f of n by g of n, where n tends to infinity, then this limit would be finite, would be less than infinite basically. And this is what I had seen. Okay. And okay, there's this lemma which is the same, I believe. Like this lemma just talks about it being finite. Okay, cool. So I'm gonna go to my blog real quick. I'm just gonna start adding these things. Let's see what my blog says. Started writing this post on 5th of December, bruh. 5 days before CS-6515 final exam. The final exam is optional if you are happy with your grade. I have already secured a good grade. Passing with a B in this class. Passing with a B in this class. Already secured a good grade in this class, and I do not need to do anything more to graduate. Class, and I do not need to do anything more to graduate. I also have a job lined up. And I'm also done with most of these assignments. All of these assignments. Also a job lined up, and also have a job lined up, and really excited for that. Really excited to start. So I'm left with very few convincing reasons to get this exam. I'll just list them out here for the sake of my character. Test my willpower, review mistakes that I made in previous exams, improve my neural connections, and develop a deeper understanding of the subject. Okay, anyways, cool. So, note notations. Cool. So we'll first start with notations, right? We'll go to my notes, not notes. Sorry, my bad. View draft. We'll see. We don't need to go to notes. Okay. Okay. So I'm just gonna start with notations. I'm gonna be like, this is one notations, and a lot of this is gonna be in LaTeX. So I guess I'm just gonna start making headings. Save as draft, and if I reload this draft, it's gonna be notations. Yeah, this is fine, I guess. God, this is so boring. This is just like such a test of my willpower. Man, oh man. Anyways, let's see. We'll figure it out. So the first notation I'm gonna be like is the big O. F of n equals big O of g of n. What happens if I save this as draft and I go here? Okay, this is somewhat okay, I guess. Fine, whatever. What if I do one here? Save as draft. Yeah, this is pretty decent, I guess. Yeah, pretty decent, I guess. Big O notation. I'll just write a disclaimer note. These are meant to be rough notes that will help me retain information that I've already studied in extreme depth before. Cool. Anyways, that's fine. So the first is a big O notation. The important is to focus on the fact that f of n is less than or equal to g of n. Okay. I'm just gonna be like tbh. I don't. Okay. Screw this. Why am I being so thorough, dude? Okay. Now that these are meant to be rough / shorthand notes that will help me retain information that I've already studied in extreme depth previously. Cool. So this is gonna be like save as draft. Let's see how the formatting looks. Come on, you can't take this long to just, like, annoying, bro. Okay, so in general, you should only focus on this tiny sign here that you see here, right? Like this less than equal to. You don't need to, for the purpose of exam, I just know the patterns that they would ask. So you don't need to. This is like how it's written. Important f of n is just less than. And then I'll just add the rest of the notations as well. Big omega notation is just / omega, and this is gonna be omega, and let's see, I'll just be like, okay, I just know that this is greater than equal to, that is gec, and this is just strict equality. Save as draft. Let's see if this works out. Okay, so big omega notation is let's see. So I know that in general for big omega, you need to focus on this sign. You just need to see if the f of n is greater than g of n, if g of n is less than equal to f of n, and so on. Right, that's how it works. And notice how in definition of small o, you're just getting rid of the equality. You're just saying that it's strictly smaller, and same for small omega, it's like strictly greater. That's all, right? And let's see the idea of divide, conquer, splitting problems into smaller pieces, solving the smaller problems by recursion, combine solutions for subproblems. Okay, So there's the merge sort example where we divide our input. So this is the input of size n. Every time you call a merge sort, you call it twice. Every time you call it, you shrink the input by half. Not shrink, I would say you divide the input into half chunks, and then you call the merge operation. And the merge operation in general, the merge operation is going to take how long? It's going to take linear time, right? So if you have k in this left call and k in right call, then it should just take 2k time to perform the merge step, which is fine. Compare the first element of L and R, append the smaller element to the output, and remove it from the left. Okay, fine, whatever. Claim if okay. So this is interesting because this is also the part of your theorem proving. So if L and R are sorted, then merge LR returns a sorted array. Fair. So this is basically important just in terms of I would say, what is this important for, honestly? Is this important in any form or shape? Let's see. This is just a good way to structure your proofs. If any of your proofs require induction, then you could do this. So you know what? I can just do this. Coverage. So PDF coverage. Okay, so one is notation and structure for induction. Fine. We'll just I guess I'll just do this for example. I just find one here. So the first one has structure for induction. Let's just see structure for induction. I know we have a base case where you just say that for the smallest possible input size, you can be verbose and just say that it's correct. Your hypothesis, set n such that merge sort correctly sorts all arrays of length less than equal to n. Okay, perfect. So your hypothesis is not going to be true. Your hypothesis assumes that up to certain input, up to like a certain size, up to like certain input size, your what am I even fucking saying, bro? Up to a certain fucking input size, your algorithm works correctly, and then you assume that after a particular input size, shit goes south, shit breaks down, and then that's when you either disprove or prove. So let's see, like the hypothesis, the induction step says that merge sort. Okay, so this is again like a very argumentative thing. You're saying that your left and the right. Okay, let A be the array of size n plus 1, left be this, is correctly sorted since this is this. Okay. This is easy because it's saying that, hey, our hypothesis says that anything with size less than n is correctly sorted. So it's saying that any array of size n. So the thing with hypothesis step, like the second step of induction, is that when you're doing the final step where you're doing the proof, you should be able to use the induction step to kind of say that, hey, you know what, bro, because my hypothesis said so. Okay, you know what, this is a good pattern. I'll just write it down in my blog. Notation is pretty easy. Proofs by induction. Let me just write a note. This is not gonna be directly tested, but there are standard patterns in proofs by induction that you can simply use in your in your exams. So I'm just gonna be like base case easiest. So this is gonna be easiest uh, part where you argue why algorithm is right for input size 1 or 0 or whatever is base level input. You will get partial marks here, so don't fumble this, right? So don't fumble this. 2 is hypothesis. State that up. Okay. Hypothesis. This has several pattern. Pattern 1. Algo holds true for inputs up to size n. Pattern 2, algo holds true for inputs. Hold on, actually, you know what? There's just one pattern. Claim that the algo holds true for inputs up to size 1. 3. Proof by induction. This has patterns. So pattern 1 is pattern 1 is claim that argue how problem changes with input n plus 1 and use claim in step 2 to argue why. So I need to be more eloquent here. I need to be better at explaining what I'm doing here. So again, the hypothesis section is always we assume that up to input n everything is working correctly, or everything works correctly. So what we gotta say is argue how problem changes for input n plus 1 and use the claim in step 2 to state that everything up to n, up to input size n works correctly, hence argument 1, hence argument 1 naturally, argument 1 is also correct. Argue how problem changes with n plus. Hold on, I can just do this. N plus 1th input and how it can be solved correctly. Then use claim in step 2 to state everything up to size n was correctly. Argument 2 plus hypothesis proves is the required proof. That's one. pattern to change input to 2n maybe, and follow the previous method. Pattern 3 would be assume the opposite or contradiction and then disprove okay, and then show that hypothesis, and then show that proof must always be right. Oh, what am I saying? Proof? What does that mean? And show that proof. Okay, and show that algorithm works correctly without the contradiction and hence correct. Again, these are just rough notes, but anyway, save as drafts again. Let's see. This is not going to be tested directly, but there are going to be patterns. Fine, you will get partial marks, so don't fumble. Okay, I've just like recognized 3 patterns, but anyway, so this is a crucial one. So anyways, like, you know what, like one easy way to get away with this, get away with some partial marks, is just claim. Here you can see that the crux of this proof lies in the proof of claim, where you say the merge of L and R, compare everything, whatever, and remove it from the list. Okay, so it's like append smaller element to the output. So it's just verbose, it's just describing what's happening. Must be bigger than the elements, right? This argument holds for all inputs, sure. So it's just claiming why merge works and not. So you see the step, the induction step, right? The induction step. I'll just say induction step. So induction step is usually like a standard way to say that, okay, the next step is going to be working like this. So in this, I can just say that induction step is just going to work. This is just the first 5 lines are just claiming that, hey, left and the right works, like my sub is working. The actual crux is in the merge, I would say. This is also pretty clever, but I can see how I can get away with some partial marking. Cool, so I'm done with divide and conquer. It's pretty decent. Let's go to divide and conquer 2. Let's see how much time we spent. Like it's 12:26. So 12:26 a.m. What did I do in 12:26 a.m.? Finished PDF 1. Okay, so I think it could have. Okay, let's see. So it took me 23 minutes to work on get through PDF 1 and do blogging and bullshit. But anyways, I get it that I can do faster. I can do much faster, right? Structure / patterns. That's fine. Now, let's go to 2 complexity analysis. This is just analysis of merge. So, okay, this is like Master's theorem, I believe. So in Master's theorem, what do I need to keep in mind? Okay, so I don't need to keep in mind a lot of things. I'm just gonna be like, okay, so I'll go here. I'll be like 3. I'll be like Master's theorem. I just need to remember some basic results to solve short questions. Anyways, so Master's theorem. Okay, this is the recursion tree. Okay, so let's just like a few notes, I guess. Uh, okay, hold on. All right. I know to calculate this. This is fine. This is fine. This is fine. Big O of C into the power I. Okay, this is actually a pretty decent one. I get it. This is like the input size, the nodes. Okay. Okay. So okay. The okay. The this is mostly used to uh, quickly figure out time complexities, figure out runtimes of what does it do? Okay, just quickly used to figure out the runtimes of some functions, some functions, some recursive functions. Okay, some recursive functions. Uh, the form it takes is this: Tn is just gonna be equal to a dot t of n by b plus big O of n to the power c, I believe. Uh-huh. Okay, so let's see. Save as draft. How does this render? Master's theorem. Okay. Yeah, looks pretty decent, I guess. Okay. Okay, so so I'll just like maybe just note things down. When we unroll a recursion tree, then on ith level of the tree, the input size is again input size is n by b to the power I believe, right? When we unroll the recursion at the ith level, the number of nodes slash vertices are dollar a to the power I believe that's how it is. Yeah, I guess that's how it is. And then 3, let's see. When you enroll a recursion tree, then on the ith level of the tree, the total work done is total time spent is just this thing, n to the power c summation of from I going to 0, my bad, to I think it's like log base b to the power n times like a by b to the power c to the power I believe. Save this as draft. Okay. Hey, oh, bro, shouldn't this be like a save this as draft? Bro, what the sigma? Come on, bro. I didn't know that you did that to people, bro. That's a dick move, right? Bro, what the sigma, bro? No, okay, this is decent, I guess, but I didn't know that it needs this level of Anyways, okay, let's see. So all merges in this layer, ith layer, uh, time spent in one vertex. Okay, is this the total time? No. Is it the total time? Okay, let's see. This is the time spent in ith layer, right? Like, okay. Time spent is big O of whatever that thing is. N by b to the power I. So what is n by b to the power I to the power c? Let's see, I'm thinking. Let's see. So n by b to the power I, this is the input size. This is the number of vertices, fine. Okay, so the C factor is essentially telling me this is the time spent in one vertex. Okay, so over all layers. Okay, so then I'll just say in all layers the total time spent okay. Across all the layers and nodes, the total time spent is this, which makes sense, I guess. You're just doing like a summation of these things, I guess, right? Let's see, how does this make sense, right? Like, this is the time spent in one layer. I get this part where you are okay, so I get this part, you're just taking a inside and moving into the power c as a constant outside, and then this stays the same, and the three cases where you just need to note this down. Okay, so there are three cases for Master's theorem. One, A equally, okay, hold on dog. A equals b to the power c, and the time complexity is big O of n log of n to the power, say c, log of n. That's equality. If there is a is less than this, then it's just n to the power c, and if a is bigger than this, then it's n to the power log of log of a. That's how it should be, I guess. Let's see if this works. So it has this rendered. There are three cases of Master's theorem. A equals b is n c log n. A less than b is this. Okay, so let's see. A equals b n c log n c, and log b a. Perfect. Greater than. Perfect. Cool. What else do we have here? We have the max diff. What does max diff say? Okay, find the maximum difference between left and right. So why did we do it with divide and conquer? How do I even recognize if the question is prompting me to do divide and conquer? Let's see. I think in general they give the heading for every section. Like, for example, this like says complexity. So I think the professors would be kind enough to give us a nudge, or at least give us some sort of like heading that, hey, you know what, this question pertains to this particular this particular concept, maybe. I think that should be fine, I guess. So let's see, there's 40 points. This is how many points? There's 35 points? Really? Bro, 35 points is crazy. I know there's gonna be some like divide and conquer analysis, which is gonna be easy. We gotta write a dual for something. Okay, whatever, 6 points is crazy small. There's a DP question, which is so they're gonna have like section wise things, like they're gonna tell us what is DP, what is dynamic programming. Okay, fine. I hope they don't like give us like extreme proof based questions. Okay. Okay. Okay, fine. Fine grained complexity is just gonna be OV conjecture. Gonna be some reductions, I guess, given complexity of analysis. Correctness of your reduction. Fine, bro. If there is an orthogonal pair, I guess something happens. Fine, whatever, bro. Fine. So I think Master's theorem should be this. Should be it for Master's theorem. Let's see. What does max diff do? It's just gonna be some left and right. The trick here is you add like a middle thing in the middle. You do max right. Suppose you find a max in the left half, max in the right half. What is it that you need to do? It's either going to be a max in left half, it's either going to be a max in the right half, or it could be in the middle that crosses the center, right? What does that mean, right? So you need the maximum on the left and the minimum on the right, so that you can take a difference of those things. And we are saying that there could be one case where the max difference crosses over the center, and for that you're just like doing an iteration. And for that iteration, you're saying that, hey, you know what? I can maintain some. Okay, you're just doing Master's theorem here. Okay. Cool, fine. So 2 was pretty straightforward. I'm just gonna note down what I learned from 2. Master's theorem and max diff. So let's see, it took us 12:41 a.m. Finished PDF 2. So 15 minutes to do 2, which is still not really ideal, but whatever, right? This is gonna be a bit harder, I believe. It's gonna be polynomial multiplication. But fine, let's just go through polynomial multiplication and see how it goes. Whatever, right? This is gonna be topic 4, which is polynomial multiplication. Right, let's see. So okay, this is like the representation of the degrees. Let's see, I had written it down somewhere, right? Or fast Fourier transform or polynomial multiplication, for example, in general, right? I knew it that they have like this. I knew that they had this like syntax thingy in this, right? So, because that's what they had asked last time. I remember that they had asked for the syntax last time. Well, syntax is just the representation. And I was like, okay, bro, sure, bro. Whatever, bro. You know, bro. You know how it is, bro. Anyways. Bruh. Okay, cool. So let's see. Mm, okay, so let's just say that it's gonna take us 2 days at least to. What am I doing? Okay. Okay, so let's see polynomial multiplication. Let's see. What am I doing? Okay, like I'll go through this PDF and I'm thinking, how should I work on this, right? Let's see. Let's see. Uh, strategy one could just be to strategy one could just be to write things down, right? I'm a motherfucking millionaire. What am I doing, dog? Wondering what would be the sample questions for the last unit be like pretty tough, I would say. So you do f of x equals some xi f of I, and you have like d such polynomials. Like, sure, a polynomial of a degree d can be something of this sort. Sure, makes sense. And okay. That's just one polynomial, and if there are two polynomials and we're trying to multiply them, like the one I'm doing for 2x4 to the rest of these things. Okay, let's see, thinking. Okay, I get it. So what's worth noting down here, right? I think I get it. Oh my god, bro, my body hurts, bro. My body is just sore because of all the workouts I've done. But whatever, right? Whatever, right? So if I do this, I know that um, there's this dude who was just staring at me, and I was like, "Dude, you gotta stop staring at me, bro." Okay, anyways, let's quickly note this down. So what's important in this one is like a degree, sure. I think the representation would be pretty important. This part, especially the summation part that you see here, I think this part would be really important to note down. Right? I think this would be like really important. So okay, let's see. I can just do that. One time complexity d big O of d log d uh, where d is the degree of the polynomial. Uh, representation could be something of this sort. It could be sum of sum from I equals 0 to some d. This is going to be up. So okay, it goes from 0 to I equals d, and this is just going to be like x of I f of I, right? You multiply this with another polynomial of d, and say this is like some g of I. Let's see how this looks. So you have two polynomials of degree d, right? And two polynomials of degree d, and what you are doing is you have to represent their multiplication. You are saying, did I not save this? Yeah, okay. So there are two polynomials of degree d, xi and gi, and you're saying that their multiplication is product is represented as, okay, there are going to be two d's. I is going to be starting from 0 again, but this is going to be 2d, right? And the way the sum is going to be is x to the power I, it will be, and then it's going to be like a nested sum. So there's going to be like an outer sum of going from I to 2d, and there's going to be an inner sum going from k equals 0 to I believe. Makes sense that it will go from this to I, because every inner product would multiply with something, and this will just be g of k times f of I minus k, I believe. Sure. So I ain't gonna spend too long in like like figuring out the structure. Um, Product representation would be this, maybe 3, where I would say k is c dots I, and I minus k equals, come on dog, I c dots 0 for data structure is roughly this. f is 0, okay, sorry, 0 1 c dots d. G is the same, I believe. Sure, this is gonna be G. Next would be H. H is gonna be the same, I believe, but it's just gonna go to 2D, right? And then what do we have? We have, okay, and yeah, sure, you could do H of I. It's just gonna be for you a sum, right? Oh, hold on, hold on. I'm just trying to see if I got this right. Okay, got it. Sum of sum going from k equals 0 to some I, and this is just gonna be g of k dot f of I minus k, right? This is how we get it. Save as draft. This is the rough representation of the data structures, I would say. Now let's see. Polynomial multiplication has some examples. There is some examples. Okay, so let's just go through. I could say like some FFT tricks. I know this is used in threesome where okay, so where you have like a equals some 1 3 5 whatever equals like x plus x cube plus, hey come on, I did plus, bro, x to the power 5, for example. Then we use convolution to do then use convolution using it's fine, you use convolution. A is larger array and B is smaller array. Then for FFT, wait, what is this section called? We must flip B to get convolution. Convolution, sure. And all we're doing is we're saying that, okay, if in C, then threesome output is true, else false. Time complexity for threesome is big O of n square, I believe. No, hold on, bro. So what we're doing is we're doing fast Fourier transform in big O of, we're doing fast Fourier transform in n log n, right? And then we check okay, so big O of n d dot log d, for example. So the trick behind fast Fourier transform is, in threesome at least, is that you do a convolution, and the convolution operation takes you like d log d time. Now that you have done a convolution operation, what you need to do is you check if uh, the coefficient c in h of x is non-zero. So you have three sets, a, b's, and c is right. You wanna see if any combination of a plus b is found in c. All you gotta do is okay. All you gotta do is okay. I can be a bit more okay. You okay, okay. You have two. You have three sets A, B, and C. You have to find if sum of two elements from A and B can be found in C. Trick. If okay, okay, for C in C, if call this h of x maybe if the exponent, I believe, if coefficient of dollar $x to the power c is not non-zero in h of x, then 3 sum output is true, otherwise it's false. So save as draft. Again, it's not the cleanest, but if three sets, you have to find two elements. Okay, trick. Okay, call this h of x. For c in c, if coefficient of x to the power c is non-zero and h of x 3 sum output is true, otherwise it's false. Fine. So this is just one trick, I guess. Sure, there are other applications for this. There is a similarity application. What is similarity application doing? That's just okay, fine. This is easy. M plus n log n. This is just cross correlation, which is fine. Okay, so the coverage for this PDF is just what? Let's see. The coverage for this PDF is just, I believe, what is the coverage, bro? Okay, anyways, it's just bullshit. It's just, what is this doing? You're not just finding the closest pair, but you're also finding the okay, similarity, vector similarity was another one. Okay, so I'll go through if there is C, sure, image detection, pattern matching, similarity task. In here as well, we have made it, reversed it, okay, fine. With one polynomial flipped, sure. Coefficient is dot product of, okay. Coefficient xi in C of x is dot product of b and I plus 1, I plus m minus 1. Okay, cool. Okay. Okay. I get it. Okay. Mm-hmm. Come on, dog. This is crazy. Why do people do that? Why do people do that? Okay, anyways, let's see. Okay, anyways, so um, what was I doing? What was I thinking? What was I trying to get at? Okay, anyways, so dot product. How is this a dot product? Because B is whatever something, and it's trying to do a multiplication. Okay, the coefficient of xi in C of xi is the dot product of B. Ah, this is so interesting. This is so interesting. So we know that the okay, this is beautiful because it's such a subtle and beautiful observation. I gotta write this down honestly. Actually, I just write this down in my cheat sheet as well because it's such a good observation. How did I not see this before, right? Okay, this is a beautiful observation, honestly. A lot of things can be accomplished with this observation. So I'm just gonna write this observation down. Uh, Coefficient of xi in Cx is dot product of b times I plus 1, I plus m minus 1, where a is 1n, b is 1m, m is less than equal to n, where this is happening, and ax equals summation of ni equals 1xi ai, bx equals summation of I equals 1m xi b of m minus I, cx equals ax dot bx, I guess. Okay, perfect. Okay, so a very important observation that this is, I'm just gonna note this down. Imp observation, I'm just gonna be like, okay, A1 same is gonna be B and we'll just say that, okay, ax equals okay, I believe, and you define bfx as the sum of this, just going to m instead of n, and xi, and this will just be m minus 1, m minus I guess, right? And you define your c of x equals then coefficient of is dot product of b dot a I plus 1 c dots I plus m minus 1. So again, a very interesting observation. If you are ever doing this, like I just know that the ith, or I just know the meaning, right? I just know the so I kind of now know the intuition behind a particular multiplication, I guess. Have I written this down somewhere below? Oh, I had written this down, but I just never paid attention to it, I guess. Okay, I guess. Okay, I guess that's good enough. And what does this do? Nothing, that's it. So that's all we had. Let's see. 3 I'm closing. Let's see. It took me 1:13 a.m. Finished PDF 3. So okay. So it took me almost what? This was what? 19, 20, 32 minutes. 32 minutes, I guess. 32 minutes. Well, I guess into bed. Uh, yeah. Polymalt syntax. 3 sum tricks. Uh, Representation and observations. I guess that's what I got from this. Okay. Cool. So let's go to fourth now. Fourth is this something that we've already done. F could be stored as an array, sure. XIFI, sure. Had I written this down somewhere? So this is the representation. This is the point representation. Okay, sure. I know for a fact that this ain't gonna show up because they did mention that you won't have to go through this shit. This I've already covered. This I've already covered. The idea of algorithm is not something that we need to worry about because it's just theoretical that we never had to worry about. We were told about this. D log D multiply y coordinates to get point rep. Okay, fine, D log D time. Sure, so I know that 4 I don't need to go through this, so I'm just gonna be like, okay. 16 a.m. Finished PDF 4. FFT theory THEORY that we know for sure is not going to be on test. So again, we're fine with not doing 4 because it's just like theoretical stuff that's not gonna anyways come on the exam, so that's fine. Okay, cool. Man, there was another good FFT trick that I forgot. Like, it had to do with, was it like closest pairs, I guess? It was closest pairs. I don't know why I did not pay attention to that. But fuck it. Okay. Skibidi. Skibidi. Oh, skibidi re. Okay, so first exam was whatever. That's just old shiz, bro. There's some topological cycle detection. Do I need to do anything important here? Is my question. Sure, there's some DFS, BFS topological order shit. Okay, let's do that. I'll add more if I remember. Okay, DFS, BFS, topological order. Okay, let's see, let's go through this. So we have given a graph, adjacency list. Every vertex has a list of neighbors. Sure, matrix has something else. Okay, so if we have vertices, sure, you mark it as one. List is just this. Typically easier for adjacency lists. A simple DFS traversal is visited. You add it as true for like the children of V in edges. Okay, for whatever children of V there are, for every neighbor of V, every neighbor of V, if it's not visited, you do DFS of D. Okay, and we know that all vertices. Okay, sure. Let's just do that, I guess. DFS slash BFS runtime is just gonna be like a big O of E, right? Now there are edge types like what is. Wait, are you telling me that I had never written down the edge categorizations anywhere? There's no way, bro. Forward if A visited before D. Cross edge if A visited after D. Okay, whatever. Edge types, I guess. Okay. C edge. Edges used by DFS to recurse. Fine, I get it. Then there is a back edge. What is a back edge? Let's see. Okay, let's just do post order first. Order of vertices so that all edges go left to right. Sorting by post order in descending direction gives a valid topological order. That's what I know. Back edge, then we have a forward edge. AD forward if A visited before D. Cross edge A D cross edge if A visited after D. Okay. Back edge is what? Okay, let's see. So green edges are this. Back edge is when post order का edge is after you're visiting something that is already visited. Visiting something already visited before, right? So you have a DFS का algo. Dog, come on, dog. Who is Saurabh Kumar? Why does he want to connect with me? Why do people in general want to connect with me, bro? Who is this kid, man? Okay, he looks cool, honestly. He's like an IT Roorkee kid. Loves competitive programming. I can respect that, bro. He's a quantitative trader that's actually badass. Oh my god, I gotta connect with this dude. Research scientist for 14 years, then founder. Okay, pretty good, bro. Man, oh man. Okay, so let's see. Well, I have studied for sure. Okay, let's see. So the pre-order array is the array in which we track the visits. Post-order array is the array in which we track exits. So for a neighbor in U and V, we have a pre-counter and a post-counter, and we have a pre-counter and a post-counter. fine. Whenever we see neighbor of one, we start with some random vertex, and for all neighbor u's of vertex v, if it's not visited, you do DFS. Otherwise, every time you visit, you say pre-counter 1. So it's like whenever you visit it, you increment its counter for the first time. If okay, so if post order u is 0, if the child is already visited, post order of u is 0, as in like, oh, okay, I get it. Ah, my god, bro, my body hurts cause of extreme. Okay, anyways, I see. Note that you will have to refer to the algorithm at the end of this section. Back edge, right? If you find an edge that connects to a vertex that hasn't finished its traversal, then it's a back edge. Or if post order edge, if post order of u equals 0, then it's a back edge. Back edge where u is the neighbor of some vertex we are currently visiting, right? And we are saying in our algorithm, we were saying that if the pre-order is greater than the pre-order of v, that is, if its neighbor has been already visited, it's a forward edge. Why is it a forward edge? You will see. If the pre-order is greater than the pre-order of v, u is the neighbor. Wait, shouldn't this be the other way around then? If pre-order of u is greater than pre-order of v, u is the neighbor. So I found an edge from d to u that says that, okay, see, okay. Oh, okay. I see now. So A to V is the one. So okay. Pre-order of U. Pre-order V. Basically, this is the condition. And cross edge. Let me just see cross edge. Right. Cross edge is saying that, hey, listen. The post order, I'm saying that this is completed its visitation. So it's just else. Is this else case? Okay. The algorithm roughly looks like this. I'm just gonna like Python maybe. Pre-order equals 0 times in, post order equals 0 times in, whatever dog, whatever bro. Pre counter equals 0, post counter equals 0, def dfs of some v. We just gotta be like hey da 1 2 3 4 non-local pre-order, post order, pre-counter, post counter, and so on. If of course visited equals this. If visited v equals true. Okay, just mark it as true first of all. Okay, you say visited v is true, and then you are saying that okay, pre-order of v equals pre-counter plus equals 1 for neighbor u of v, neighbor of v, if not visited of v, 1 2 3 4 dfs of u. Cool. ट्री एज, ठीक है. इफ नॉट इजिटेड ऑफ यू है क्या? यू होना चाहिए, राइट? ये यू होना चाहिए, ठीक है. There's one correction here which will be like okay, ठीक है. Then it will be like elif post order of u. अगर ये 0 हो गया, vu is a back edge. Elif pre-order of u greater than pre-order of say v, v and u is forward edge. Like else is just gonna be like whatever, right? View is a cross edge, okay? Cross edge, and then we just do post order of v equals post order counter, and then you just do post order counter, right? That's how you do it. Save as draft. Okay, pretty good. Cool. So topological order is this. So A, B, C, and D है. So A, E, A, B, B से D, and B से C. So makes sense. Okay. Okay. So DFS versus BFS में you just gotta do like DFS and BFS just has like stack and queue thing difference, I guess. uh, philo is just algo behaves like a stack, that is DFS. FIFO algo behaves like a queue, DFS, right? Save as draft. So let's see. So you just do queue.add. This is just a random queue, right? Any queue it could be. While queue, you add something to the queue. While queue is not empty, you just do queue.pop. If there it is visited, okay. While queue is empty, not empty, you get from something in the queue. If it's visited, you just do the next one. You said visitor is equals to, for its neighbors, you just append it back to the queue. Cool. Cool. So what did we do? We just did fifth one completely. So let's just go here. It's just like DFS, BFS, topological order, FIFO, philo. What else did we do? Pre-order and like post-order. Cool. Let's see. So it took us till 1:40 a.m. finish PDF 5, right? So okay, so 24 minutes to finish PDF 5. So not too bad. Like I'm running through these PDFs in like a few minutes, which is pretty good, right? Yeah. Anyways, let's see. There is some search questions we have. Sure. Priority queue is when tons of different priority queues is like heaps and shiz, bro. Whatever, bro. We have this Dijkstra thing, and we have some bottleneck path things. I know Dijkstra is gonna be asked, so I might as well do Dijkstra. I'll just do like a section on source algorithms maybe then. Yes, queen. Yes, queen, you tell him, queen. Say what's draft, baby. Say what's draft, baby. Yo. So, okay, search algorithms, we have queue.add, fine. If visited, you do like next, sure, whatever. Otherwise, you say, hey, I've just visited this. And you check all these neighbors and then queue it, sure, whatever. So you start and you F distance 3. Observation for vertices of distance less than equal to t before visiting a vertex of distance d plus 1. Fine, whatever. Find the shortest path s to every other vertex, sure. Use the same algorithm, but use distance as priority. Okay, so we have Dijkstra this time, but we have like a distance parameter. So we have a theorem that we can just use, I guess. Note that these results can be directly used in exams. So theorem is Dijkstra's algorithm finds the shortest path from start vertex to every other vertex. Okay. Dijkstra's algorithm finds the shortest path from start vertex to every other vertex. From start vertex to every other vertex. If the graph has only positive edge weights, okay, so for some v distance is indeed the length of the shortest path. Okay, so there's some proof of Dijkstra we don't need to go into. It's just proof with contradiction. whatever. Sure. I don't want to change my bulleting in the middle. So I know that Dijkstra's algorithm uses distance as a priority in priority queue. That's what Dijkstra uses, and the algorithm is roughly this. I'm just gonna write some pseudocode here. Def ti jks3. So what are we taking in to Dijkstra as input? Like we're taking into our input as some source. We're saying q dot add null and 0. So we're adding our source vertex an empty set and 0 to the queue. We are saying my distance of s, distance to my source vertex is 0 is what I'm claiming. While queue not empty, I am saying something. V and parent so I'm saying pop out the lowest priority value, shortest distance. We're basically being greedy here, right? And then if visited, if visited, that vertex is visited, then we say continue. Otherwise we say visited v equals true. Sure, this is something that we need to do for sure. And distance of v is gonna be equal to distance of parent. Right, this is the parent that we get, and this is like this is gonna be like one tuple, I guess. Current, parent, and distance. Right. And I'm gonna be like, okay, distance is distance from its parent. So I have like a distance queue which says, okay, how far away is distance from source? I'm gonna be like cost of okay. So I'm saying the distance v is so it's always gonna look for distance from source to parent. Okay, fair. For neighbor u of v, q dot add u v distance of v, cost of view. Okay, v is parent and the last param is the priority, right? So let me see. So we added to the queue the current, parent, distance slash priority. This is technically the first element that goes into the queue. then you get you pop something from the queue, you pop the lowest priority thing from the queue, and you say, hey, if it's visited, you continue. Otherwise, you say distance is going to be distance from its parent plus cost of parent plus v. Yeah, I think this could work. Okay, I get it though. Hmm. What is a bottleneck path? Uh, there's Dijkstra, there's bottleneck path, which is the same. Smallest possible sum of edge weights. Smallest possible sum of edge weights. Okay. Okay. So min spanning tree. Okay, this is like PDF 6, right? So after I finish my PDF 6, I can just take like a small break, I guess. So I know for a fact that bottleneck path and all won't be asked, but I'm just gonna add it anyways, right? Cause that's what good boys do. So bottleneck path is smallest edge weight on the path. Smallest edge weight on the path is, say, this. Send at most 11 tons. Find the longest path. Longest path? Do you want the longest path, dog? Bro, why would you want the longest? Fair, sure. Okay, let's just see. What in graphs, what is a bottleneck path? By the edge with smallest weight. Okay, got it. I get it. Okay, I guess. So bottleneck paths, bro. This is the real shit. So see, I can finish this today. It should be easy, I guess. Should be easy. It should be very easy. I'll sleep for a while, wake up around noon, make some food again, I guess. And then I will perhaps. Yeah, whatever, bro. Whatever, bro. Cool. So bottleneck path. Let's see. Length is the smallest uh, edge weight on the path. Bottleneck path. Basically, find path with that allows carrying max amount of flow, maybe. Whatever, bro. Algo is roughly this. Okay, so algo is, it's not even Python, it's just some pseudocode, right? S null and 0 maybe. So it's pretty much the same as this one, I would say, right? So what changes here is highest priority, largest edge, and the distance function this time is just min of your parent and the cost. Wow, this is just different this time. Just प्लस के जगह पे तुम min कर रहे हो और इसमें भी तुम बस min कर रहे हो. That's what you're doing. So the only difference between bottleneck path and this is when you are pushing, when your distance calculation you're doing. Okay, cool. Min spanning tree of G is a spanning tree of G with smallest possible sum of. Okay, I get min spanning tree का फंडा भी समझ चुका हूँ मैं. Okay. Okay, this is just the intuition for Prim's algo is roughly this. So it's just small modifications to every algo. Prim, you have the Q, you don't need the distance metric here. Ain't gonna be used. So while Q is not empty, you just do a pop. A site visited equals to. Now what you do is T equals T union V comma parent. Okay. Okay. And finally we have A star algo is some heuristic based search algo. Algorithm is roughly this. You do need this setup here. In A star you're saying the distance and all these are all the same. Well, Q is not empty. Sure, you need lowest, smallest edge. Okay, smallest heuristic value. If distance v, now this changes if distance v is greater than distance of parent plus cost of parent to v, you found a new path basically, right? Found a new smaller path. Else okay, तुम करो है हो ये distance plus cost plus थोड़ा सिंटैक्स हाईलाइटिंग क्यूट लगेगा ना, तो कर लूँगा मैं सिंटैक्स हाईलाइटिंग, ठीक है। ठीक है, so that's how A star should work, I guess, and I think that's good. So A star में क्या हो रहा है कि you simply check if the distance, how are you updating the distance? You're saying distance is just distance from parent, sure, शुरुआत में 0 है, plus cost of parent to that v, and तुम जब ऐड कर रहे हो तुम बोल रहे हो they're just adding priorities first of all. Okay. So okay, got it. Let's see. Dijkstra bottleneck prim min spanning tree spanning tree A star algo. Put these, okay. Cheat sheet needs update. Okay. So let's see, I took 2:02 AM finished PDF 6 for example. So this roughly took me what, 22 minutes? 22 minutes, 23, 22 minutes is pretty decent, I guess. So 20, 20, 20, this is like an hour to finish 3 PDFs. Again 20, so 6 PDFs take me 2 hours to finish, I guess. So 11 Ks, okays. Okay, papi. Okay, papi. Cool, so I'm done with 6th also, so I'm just gonna load up the next few PDFs. What is this shit, bro? What is this shit, bro? Yeah, I do need to cool. Let's see. Did it till 6, so the next few are Okay, actually, you know what? Matchings, I guess. So copy link, I would say, I guess. मैचिंग्स हो गया, फिर मैक्स फ्लो हो गया, फिर वन लिंक न्यू टैब, मैक्स फ्लो हो गया, राइट. Let's see, this is matchings, this is max flow, this is linear programming, I guess. Yep. Sure. Closing this. Linear programming हो गया, LP duality, copy link. This is LP duality, dynamic programming, copy link. Cool. Dynamic programming. This is a YouTube video which I don't want to watch. Copy link, I guess. Knapsack MDP is copy link. Okay, so 1 2 3 4 5 6 7. Yeah, MDPs are pretty bad too, bro. Okay, anyway, so let's see. MDPs are done. Simplex is fine. Simplex is like the last few parts. So from simplex to this is just gonna be some other stuff, I guess. So these are from what to what, right? 7 8 9 10 11. Wait, we need to do 7 8 9 10 11 12 13. So 7 to 13, I guess we need to do. Okay, let's go to the online notepad. Let's write this shit down. I'll do this later on at the end. Maybe, you know. Cool, I have blogged about these things. I do not have the time to do this, but whatever. Finish going through PDF 07 to 13 from matchings to what? Markov decision processes. Okay, Markov decision processes, I guess. Review exam 1, exam 2 and exam 3 mistakes. Cool. Cool. So what I'm gonna do is I'm gonna take a few minutes break, I guess. Where is this? On a short break, baby girl. Woohoo! Okay, on a short break. Cool. Excel. Oh, come on, bro. That's so stupid, bro. Okay, I guess. So I'll be taking a short break. and then I will grind through. I know it will take me 2 more hours, so 2 more hours, around 3 more hours to go through everything in Unit 2. Honestly, I don't know how big Unit 2 is. Like, I just know there's some matching stuff. Actually, no, I'm wrong. There's just a lot of stuff in Unit 2. There's just so many things in Unit 2. It's the most comprehensive shit that you could ever find is gonna be in Unit 2. So, you know, we'll come to it in a bit. Okay, some interns looking for. I saw all of okay, go. Actually move to a new. Q, somebody reached out. Sure, bro, sure. What is my team even gonna be? Let's see. Okay, I'm gonna delete the resume because I don't wanna, like. Sure, bro. Oh, what is this? This is interesting. Oh, it's a CF42. Okay. Looks pretty good, not gonna lie, dog. Okay, let's just see what I'm gonna be doing. Sure, this is beautiful. This is beautiful. Cool, I love it. Yay, so cool, so cool. Cool, let's see. Uh, Hold on. Okay, monthly, pretty good, pretty good. Yeah, pretty good, I guess. Okay. So, wow, okay. Q. Okay, let's see. Okay, I see. 2020, not 2020. I want something recent, dude. Ooh la la. Lambda and CloudWatch. Okay, interesting. Okay, sure. Come on, dog. Don't do that to me, dog. Okay, I guess. Nah, bro, come on. Don't do that to me, dude. Fine, I guess that's what it is, I guess. Let's see. If I had my. Okay, so I know this is what I had. Okay. Wow, okay. Okay, cool. 1 week every 2 months. Pretty decent, I would say. Okay. Okay, I guess. Sure. Okay, I guess. Okay. Okay. Is SDE to L5? Amazon staff and level. Oh my god, dude. There's no level 9. Why? That's so stupid. Right? Well, I guess, friends, what is this, right? Discard. Okay, hold on. Discard, bro. Discard, bro. No, I don't want Canada, bro. AWS. That's all we need to do, right? Just show me AWS, bro. Sure, 10 million followers. Let's just see people in this beach though. Hold on. I know connections been working here. Sure, bro. This guy, the principal is crazy. Not gonna lie, bro. This guy's aura, bro. That's crazy, bro. 4 years as an ST2, 4 years as an senior software engineer, and then this man just made it. Okay, cool. Let's see more. Okay, let's see more. Okay. I mean, the money's good, I guess, but no, bro. Yeah, I just want to like filter on people. That's so cool. There's like a. Hmm. I see now. I see now. Okay, I see now. Okay, okay, okay. What if I just do stuff? Man, she's a senior ST. Crazy, dude. But why can I? Okay, hold on. I just looked for stuff. Hmm. Okay. Okay, let's just do. Hmm. Okay. Hold on, dog. Hold on, dog. Hold on, dog. Cool. So I'm still on my short break. It's still pretty short, right? Container stuff is AWS. Here's a Georgia Tech. That's pretty good, I guess. Pretty good, I guess. Yeah, I think it's pretty good. Hold on, bro. Yeah, bro. Matt, Mer, Jayant. No, hold on. No, let's go to AWS first. No, just AWS. I just wanna find a dude named Jayant, I guess. 'Let's try someone named Shiv. Right. Let's see if there's a Shiv Jeet here, right? Like, that'll be funny. Nah, there ain't nothing. 4 years, that's crazy. Someone finishing a PhD in 4 years is insane, dog. Man just returned. Okay, sure, bro. Okay, there's no epic though. Cool. What if I just look for this word cool? Man, this dude looks cool, I guess. Oh my god, my man just did a PhD, dog. That's crazy. Okay. This person has cool in their bio. Is cool, I guess. Wait a minute, bro. Cool, I guess. I love this guy, man. This is so fun. Pijmon, Kasravi. I love this guy. This is aura, bro. Oh my god, I love this guy already because this guy is just aura, bro. Nah, man, this guy got aura, bro. Cool is fine. Okay, hold on, bro. Vijayasaini. Okay, cool, Vijayasaini. Whatever, dog. I don't know, dog. Yeah, don't. Yeah, exactly. Don't do that. Yeah, then don't do that to yourself, girl. Anyways, we gotta get to work now. Fun thing. What's up, Jesus? Thank you, Jesus. You're crazy, bro. Okay, cool. Let's get back to work. It was a huge air break, bro. Huge air break, bro. Bro, come on, bro. Let's get it back, okay? Man, almost a 2 hour break. Almost a 2 hour. Oh, almost an hour break. That's fine. Back from the break. Damn, I thought it would be short, but it was real long. Shorty. Shorty. Okay, cool. So, what have I done so far? I've completed the PDFs, which is pretty good, I guess. 3 to 4, 45, 3 to 4, 45, 3 to 4, 45. Cool. Uh, Thank you. Thank you for the ting, I guess. Now, what we gotta do is we gotta go to 7th and let's just see where it takes us. Okay. Yeah, I'll go with like 5 or something. I'll get like a nice naan. Right, I'll just do like a quick shower at 5. 3 to 4, 4 to 5, right? It's 2 hours, I guess. So 2 hours, we'll have to do like a pretty good focused study. So, like, agar I'm able to finish these PDFs till, yeah, by the time I reach, it's anyways just a revision. It's nothing crazy that I'm doing. I'm just going through my cheat sheet, seeing if I'm just refreshing the topic in my head right now. Okay, da. Maybe I should go pee and fill some water and then I can just get into this. It's not too bad, honestly. This bipartite graph of stuff is actually pretty easy. The actual blogging part's gonna be a bit painful because, of course, a man's just gotta blog it, right? And my blogs are actually okay. 5 reads today, fine, I guess. I've never caught someone actually in the process of reading my blog, so just kind of sad, I guess. Anyways, uh, SHV, sure. Cool dump of my notes, sure. Okay, let's go. Okay. Okay, so I'm just going through this matchings. Okay, this lecture is not what. Fine. I don't give a fuck now. Okay. Okay. So we'll just make a section for matchings now. Save draft. Save draft. Okay. I'm just thinking, is there like a more efficient or like a better way of. Hold on. I know we have to do matchings. There are some theorems around matchings. Then there's min flow, max flow shit. There's forward Fulkerson algorithm. There's capacity scaling. There'll be solvability. There'll be optimality. There's dynamic programming. Dynamic programming ain't gonna be too bad, honestly. Not gonna lie, dog. Polytime and pseudo polytime algorithms. There's knapsack. There's gonna be the pseudo polynomial knapsack questions. Okay. There's gonna be PTAS, FPTAS. Shit that we get after this. Okay. Okay, hold on. I'm just gonna go pee. And then I'm gonna go refill my water bottle. And then I'm gonna be back. BRB. BRB. Okay, I'm back. I'm gonna be back in a few more minutes. Okay, I'm back. I'm back. I'm back. I have more water. Honestly, bro, this is painful, bro. Okay, we'll see. We don't have to be super thorough with this, I guess. We'll try our best. We'll try our best. Right? We'll try our best till maybe 4. And then around 4 will bounce, I guess. We'll see however many of these we can cover till 4, which is just 43 minutes. We should be okay. I'm just gonna be quickly doing a hacker check. Just a command runner. Okay, sure, bro. Sun drenched Americana. Sure, bro. Okay. Okay, okay. Then I'm trying to quit my job to make my resolutions make $1 million in revenue in 2025. Okay, sure. Okay, let's see. Oh boy, okay. I like this. I love this so much. This is so cool. Home. Mm. Okay, let's see. Now, okay, let's see. I'm thinking. I'm thinking. Nah, man. You just gotta live life, dog. Okay, I guess. That's life, I guess. Experience dot grable. Sure, grable. Cool, anyways. Anyways. So let's see. Why should we even? Okay, hold on. So, 3:22 a.m. What is happening? Uh, Procrastinated and heavily sleep deprived right now. Need to get back into the zone for next 1.5 hours. Okay. Here is the thing, okay? Motivation. Let's figure out why we are not able to study right now. Okay. Uh, Feeling overwhelmed with the material that I need to cover. Lot of PDFs still, and okay, lot of PDFs to go through, and it's exhausting. Cool. Motivation and self debugging, I would say. Okay. So the thing is, I don't need to be stressed so much, right? But the thing is, the act of going through such tedious amounts of material, that's like overwhelming. It's like there's so much material to go through. Or I could rephrase it. I could re, I could change my mindset, you know, and I could be like, hey, uh, let's see how much I can cover using my superior intellect, right? Honestly, I hate studying. That's one. I hate studying. I just love making money. Money is what I want the most in life. Okay, like as a man, as a man, what I want the most is money. And this work that I'm doing here, it just goes completely in a direction that is opposite of money. Sure, this is a pretty complicated material that I must study and learn. If I'm ever doing a PhD at some point in the future, I do need to come back here. But let's see. Let's see. Mm, the problem is, if I do decide to start a PhD, then it will just be hyper painful, because I'll have to retake all these core subjects and so on and so forth, which I don't really want to do. It's so much math and shit. Again, I'm not afraid of math. I'm just tired of examinations. Like, I don't want to do exams, bro. Just fucking boring, bro. But, anyways, why are we working hard? What is it that I'm gonna get out of this one extra hour of pushing myself and studying hard, right? What is it that I'm gonna get? Why am I working hard? That's the question. Why am I working hard? Do I have a wife or a family to support? Wife, family? No. So the thing is, we know in general that if man has meaning, man's suffering has meaning, then man can take huge amounts of suffering, right? So my inability to study right now mostly stems from a lack of meaning. Like, sure, I could grind harder, I could do more things, right? Uh, but anyways, that's not the point. That besides the point. I know that the next few years are hmm. Actually, why am I working hard? Paranoia, fear. If things are not perfect, I. Okay, paranoia, fear, and guilt. I cannot ignore it. I wanna have the perfect grade, I guess. God, this is so painful. I'm so sleep deprived and stressed in general. It's like the last mile, I guess. Right, it's just the last mile. I get it. Like this is what am I feeling? Let's start with that. Like, what am I feeling? Right, fatigue and overwhelmed by course content, repulsed by the amount of studying that I need to do. It's the same meaning. It's the same. Okay. The repetition is getting painful. Anyways, a man's just gotta do hard things, I guess. The problem with a PhD is that it's just too long. Okay. Anyways, this is where we are, repulsed by the amount of studying that I need to do. Repetition is getting painful. The thing is, I want to build hard, complex products. Like, I'm a builder. I want to build hard things. The thing is, I do not have the willpower or the currently not the mental energy or focus to build hard things. That's the problem. That's not good, right? I think it's all up to my decision, right? Right. 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 Right, baby, right. You're so right. You're so smart, baby. Okay, sorry. Okay, whatever happens, uh, what is it that I want to do? I want to have a bulletproof focus, bulletproof mind. Okay. Why should I be working hard? Uh, I am seeking exponential growth. I want to raise my cognitive ceiling. Um, I wanna be the best in this world, and I wanna make a shitloads of money by 32 and retire. Blush. Okay. Hmm. Honestly, I just realized that the reason why it's so hard for me to be so serious in life is because you kind of have to be dumb to take things so seriously. Um, you kind of have to have like a little poorer, lower. I don't know, bro. Like, what you're building should have some meaning, right? What you're studying, what you're building, what you're pursuing should have some meaning to it. And without that meaning, humans suffer immensely, right? So मैं एक काम करूँगा बस देख क्या यार बेटी बहुत है यार बहन का लंड भाई sorry my bad bro I should be studying. I've just hit like a honestly speaking. I'm of that age where I should be like retiring. Not gonna lie, dog, that's actually cute, dog. Anyways, dog, we gotta keep studying, dog, because if we wanna become a legend, you just gotta keep doing things that you absolutely hate doing, and then maybe one day your brain will be like, oh shit, I actually loved it. Haha. Maybe you gotta just gaslight yourself into doing things that you know. Okay, anyways, we'll go. Cool. Bro, matchings, bro. What are matchings, bro? What are matchings, bro? What are matchings, bro? Okay, let's do this. At least three of these we can try to end. Okay, so matchings is pretty small. It's not small. Fuck. It's 7 pages. This is small, I guess. It's okay, I guess. Linear programming is pretty bad. It's pretty huge, honestly. Yeah, and what is fourth? LP optimality and duality, I guess. See, the point is, I don't see any point in doing any of this shit. Okay. fine anyways. Dynamic programming is fine, I guess. And then you go to knapsack using DP, that's fine, I guess. You get the p-task and fully polynomial time algorithms, I guess. ओके जी आपको जो चाहिए वैसा ही करेंगे वैसा ही होगा जी ओके जी okay this lecture is not a part of exam 1 sure fuck you this is part of exam 4 baby girl why does God make us go through so many exams right why does God do that why do God do that though hold on this is exam 1 I don't want that I don't want that though I don't want it dog I don't want it dog problem state 8 solutions yeah screen but it's the same as exam 1 though थर्ड मेकअप एग्ज़ाम नहीं ये तो नहीं चाहिए so this is this the same graph as the one that you are seeing here ए बी सी डी ऐसा ही है ना सेम है ना ग्राफ होल्ड ऑन तो निकलो यार इसको ओके तो ग्राफ में डायरेक्शन थोड़ा उल्टा कर दिया है बस ओके we're gonna said okay sure 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 you see this is where I would lose point for sure bro you got a residual graph yeah sure gotta do this simplex algorithm shit do not use master's theorem okay 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 just looking at the question papers sample test papers I guess okay I get it are you ready are you ready are you ready mate bruh hello testing okay let's just do 30 more minutes and then I'll like end the stream because I'm hitting my attention span limit I'll just try to go through 3 PDFs maybe and that will be good enough I guess so matchings I get it matching okay okay Okay, maximal size matching augmenting path. Okay. Hey yo, hey macha, what the sigma, bro? Okay. Augmenting path given M is a path consisting of alternate master and unmatched adjacent G, matched and unmatched edges in G, and first and last vertices unmatched in M. First and last vertices unmatched in M. Okay. Okay, so very grateful for everything that I have. Okay, so I get it. The definition of augmenting paths is that it should be an alternating path of matched and unmatched edges in G. Alternate matched and unmatched edges in G. First and last vertices are unmatched. Okay. Okay. M is a max matching if there is no augmenting path. So augmenting path क्या है? Alternating matched and unmatched edges in G. So if you have a graph, G बोले तो graph, first and last vertices unmatched. So first and last vertices should be unmatched. Okay, got it. M is max matching only if this happens. Okay. Okay. What all did I write in my? Okay. Okay, let's see. So, according to my cheat sheet, let's see, edges, observation edges form cycles or paths. Okay. We can find maximizing efficiently if we can find augmenting path in polynomial time. Okay. Okay, if we can find max matching efficiently if we can find an augmenting path in polytime. Okay. How to find? Okay, so we can find a maximum matching efficiently if we can find an augmenting polytype. Okay, so how to find augmenting paths? Use Edmund's Blossom algorithm. Implementation details not on the test, I would say. Okay, bipartite graphs. Okay, partitioning V A and B such that all edges V U. Okay, one endpoint in A and one in B. Okay, we can find augmenting paths in bipartite graph and we go off. Okay, theorem. This is a theorem. We can find augmenting paths in a bipartite graph in big O of E plus big O of V. This is just Dijkstra, I would say, time. Okay, an augmenting path is odd length. An augmenting path is from an unmatched vertex in A to unmatched vertex in B. Okay, interesting. Augmenting path has an odd length. Okay, 5 plus 2 is 7. I see. So first is to find a directed from an unmatched node A to unmatched in B. Reachability problem, okay. BFS, sure. Max matching in bipartite graphs runtime is gonna be a big O of m plus n times n, I believe. Time to find a path using BFS times max number of augmenting paths. So max number of augmenting paths is going to be n, because sure, you could just have like as many edges you have, you could have as many those many unique paths, maybe, who knows. Okay, cool. Maximum flow, directed edge. Okay, fine. Okay, fine. So okay. Okay, so we got there. Hold on. I could just split it up and put it in like another section, call it max flow maybe. Yeah, that would be like a better way to like section it, I guess. I'll just call it 8 and I'll call it like what? Max flow? Maximum flow is this. This is what? Max flow and min cut, right? Max flow, min cut. Okay, max flow and min cut. Same as draft. Okay, okay. I get it. I get it. Man, and I'm so tired, bro. I'm so fucking tired, bro. Oh my god, dog. Oh my god, dog. भाई साहब. My bad. हिमावारी, क्या कर रही हो? पागल हो गई हो क्या हिमावारी? यार ये जो सेकंड यूनिट है, जो सेकंड एग्ज़ाम का सिलेबस है, बहन का लर्न बहुत ज़्यादा इंटेंस है भाई ये तो. थर्ड का तो ठीक है भाई, थर्ड तो अभी किया है कुछ ही हफ्तों पहले, तो वो थोड़ा स्टिल फ्रेश है मेमोरी में. ठीक है, मेरे ग्रेडियंट डिसेंट वगैरह था उसमें, है ना, सिंप्लेक्स वगैरह था उसमें, है ना, तो इतना बुरा तो नहीं था वो भाई. जो लास्ट स्टफ है, दैट्स गोना बी बिट क्रेजी, आई वुड से. The reductions and this and that and that and this and this and that and crazy shit. Okay. Anyways, we'll finish this PDF and then move ahead. Okay. 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 Let's see definition. Okay. Max flow definition, right? No, not flow definition. This is just flow definition. Okay. Okay. So it says um, so the flow is greater than or equal to 0 for all edges in E. Like E is the set of all edges. Then the flow is gonna be at most its capacity. The flow is gonna be at most its capacity. Flow for every edge is gonna be at most less than or equal to its like capacity E, right? For all edges in this. And then the next is the conservation of flow. For all u not in SNT सेव ड्राफ्ट, लेट्स सी इसका कैसे बनता है. ब्रो ऐसा कुछ है ही नहीं क्या? ठीक है, मेरे को क्या बता. फॉर ऑल सी नॉट इन दिस. Sum over V VUUV, right? F of VU sum of V F of UV, something of this sort. Okay, this has rendered well, so this is like the conservation of the flow. Okay. And okay, sure. Then the max flow problem is just sure, like the max flow problem is to find a flow, uh, find a flow FE that maximizes the um, F of, I guess, SU. I don't know, dog. Bro, what is, okay, hold on. Latex not equal sign. N-eq, okay. Not eq is just N-eq. Find a flow that maximizes like the flow to source or sink. That could also work, I guess. Right, and let's get more. The claim is that we can solve bipartite matching using max flow. We can solve bipartite matching using max flow. Add a source and sink vertex that connect source connects to all vertices in set A and okay, in bipartite graph vertex set A and sink connects to all vertices in bipartite graph vertex set B. Something of this sort will do, I guess. So cool. So we did this one, which is just like what? Okay, matchings, augmenting paths, bipartite matchings, and max flow definition. So I just got two definitions so far, and let's see what the timestamp is. We finished this by 4:08 a.m. Finished PDF 7. That's crazy. That's an insane skill issue. That's a huge problem, which we'll figure out honestly. So that's okay, I guess. Right. So we know max flow definition. We try Ford-Fulkerson algorithm. Ford-Fulkerson algorithm. Let's see if I have this on my cheat sheet. Let's see. Okay, hold on. Did I not go through residual graphs? Maybe. No, they've not arrived yet. Okay. Okay. Let's just do. Okay, so I can just do like residual graphs. Like same vertices V. Edges E. Okay, edges E and E have capacity of CE minus FE, fair. Capacity is going to be higher. Okay, flow. Okay. Edges minus E with capacity $FE. Cool. We'll now do like Ford-Fulkerson algorithm. Start with F. Okay. F equals 0, C dots 0. So like start with an empty flow. Create create the residual graph. Create residual graph G of F. Now find ST path P in G of F. Find ST path P in G of F. Break if no such path exists. Break if no such path exists. That means that you already found the maximal flow. Update. F equals F plus P. Okay, ये ST path है. Okay. And go to step 2. So this is your Ford-Fulkerson algorithm. Okay, run. Okay, of course, runtime for Ford-Fulkerson is big of क्या बोलते हैं इसको m plus n. M plus n is just the time required to do time required to do like augmenting fire ढूंढने में. Cool. So that should be pretty good. Okay. and we're saying that theorem for Fulkerson returns the max flow. Okay. Okay. Theorem again. Max flow is equal to min cut of a graph. Okay. Okay. That's fine, I guess. So proof, we don't care about the proof. It's just trivial. We do not give a shit about the proof. There is a polynomial time algorithm which is called what? Capacity scaling? Is that what it's called? This is min cut, right? Oh, no. Okay. 9. There exists a polynomial time algorithm that finds max ST flow in big O of m plus n times m times log c. So oh bantai, तुमको क्या दिक्कत हो रही है? So this is called what? Capacity scaling. I'm gonna call it. This is called the capacity scaling algo. Okay, this is the capacity scaling algorithm. And yeah, capacity scaling, you start with an empty flow and some delta equals c, and you say you construct a okay, let's do that though. Let's do that then though. Capacity scaling algorithm is roughly as follows. Okay. So f is 0, delta equals c. C is max capacity, while delta is greater than equal to 1. Construct residual graph hold on, so this is just gonna be something. Construct residual graph GF delta where we remove edges of GF with capacity delta. Okay, so we are keeping edges that are at least delta. Okay, keep only those edges that are at least delta amount. Find ST path in this naya delta 2.1 ऐसा आएगा that f को अपडेट करोगे f plus p times delta. Delta is basically like the capacity. Go to 1, like keep finding more and more augmenting paths basically. Else, if no st path found, 3.1 delta equals delta को delta by 2 कर दो. Runtime of capacity scaling is big of m plus n times m times log c. ठीक है, ऐसे बना दो आप. ठीक है. ऑफ कोर्स रिटर्न एफ तो नहीं किया मैंने, तो रिटर्न एफ करना पड़ता है. ओके, ठीक है. सो यू गॉट टू रिटर्न द एफ. Always returns max flow. Let's see. Okay. Okay. Some observations. Each scaling operation of delta performs two m augmentations which means that time is less than equal to so fast करता है basically log c 2m m plus n. ठीक है. और फिर क्या बोला था, at the end of any scale delta f is gonna be less than equal to f star plus m delta, and if delta equals 1, then it behaves like it बोले तो capacity scaling behaves like Ford-Fulkerson algorithm. Save as draft, and let's see if this is properly rendered. Oh, okay, I get it now. There's one tiny mistake, that is delta needs to be capital D, right? Yeah. Save ये हो गया परफेक्ट 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 बाबा, ठीक है. Okay, so at end of the delta, hey baba, yeah. So at end of the scaling, at end of the scale of delta, f is less than equal to this. Okay, fine. ये खत्म हो गया. So let's go to the notepad and be like, okay, so we're at 424, which is pretty good pace. Finished PDF 8, I guess. So 8 में क्या था? Max flow, min cut definitions, lemmas, capacity scaling algorithm, ठीक है, ये सब था. Go to the 9th one now. We saw this shit. We saw capacity scaling. We saw these lemma. Okay, there's some new shit over here. What is this? Okay, we saw this one. We saw this one. Let x be reachable from sin. Okay. Sure, this is some random shit. Okay, we get linear programming next, which is gonna be again very painful to codify, I guess. But anyways, we'll just write it down, linear programming, I guess. Save as drafts. Oh my god, stop it. So we have linear programming, which is just 9 pages long, bro. That's crazy, dog. Okay, let's see. Okay. There's LP solvability, LP optimality, some duality. There's weak duality. Okay, so duality is later on, right? LP optimality. Let's see how deep does this rabbit hole go? There's proof of LP optimality that we don't need to give a fuck about. Yeah, right. Let's see. Okay. I'm gonna write down these things that I saw. Okay. Feasible region, set of all points x satisfying all constraints. Half space is linear inequality. 3 is feasible region of LP always connected? Yes. Is a feasible region of LP always connected? Yes, that's the finding. Okay. Linear inequality, there's a smoothie example which we have seen already. Equalities are allowed in LP. Okay. Equalities are allowed in LPs. Strict inequalities are not allowed. Okay, cool. Cool. Definition of a convex region set. A set okay. Subset equals, okay. So S is subset equals some math bb of r to the power n. So okay, a set that belongs to some n-dimensional real number space is convex if x, y in S we have, if for any xy in, if for any xy in S we have alpha 1 minus for y in S okay, latex for all. Oh, for all ऐसा symbol ही है for all alpha in 0 and 1, right? This is the definition. We have alpha x plus 1 is alpha y belongs to S. Belongs to S quad for all alpha in TK. Make it sense now. And what are we saying is any LP can be solved in time that is polymerary number of input bits. Okay. Any LP can be solved in time that is polynomial in the number of input bits. Can be solved in time that is any LP can be solved in time. Any LP can be solved in time that is polynomial in the number of input bits. Okay, perfect. I don't like doing full stops, I guess. Crazy. Polycized LP always have polycized optimal solution. Why a polycized LP always have a polycized optimal will है क्या ये? Yes. Will a polycized LP always have a polycized optimal solution? Yes. Okay. Uh, Optimal solution is corner of a feasible region. Okay. Optimal solution is corner of feasible region, I guess. Extra can be written using. ठीक है, fair. There's proof of optimality. Some non-negative linear combination of constraints. Oh, interesting. Theorem. For any LP, there exists some non-negative linear combination of constraints such that LHS equals objective, RHS equals optimal value. Okay. So let's see what I learned in this one. Linear programming, definitions, lemmas, theorems. That's it, right? Okay. And I think we'll just write this down that it took us 4:36 a.m. Oh my god, bro. 4:36 a.m. Finished PDF 9, I guess. Which is pretty good. I guess. So I think we'll continue. Okay. We'll continue later. See you later, queens. Cool. I think we did we did a pretty good job at this. So I'm just gonna stop streaming. Maybe I'll just bring this in the middle. I'll do like a little dance. Bye bye. I will see you in the morning. Oh my god, this is so cringe, dog. Okay, folks.